Hello, everyone. My name is Junyao Li. I'm a PhD student from the Southern University of Science and Technology in China. And today, I'm happy to be here to present our work empowering dynamic random access of DNA storage via 384 multiplexed nanopore signatures. My topic is also about the random access, and I have to say the Jeff Nivalas group do inspire me a lot, and our group started a lot of researchers by him, and let's go on. As we all know, the DNA is a great medium for the long-time data storage, and its stability can last of thousands of years. From this chart, we can see that the potential of DNA storage density is millions of times greater than the current technologies. And for the DNA practice, for the DNA storage to be truly practical, we have to find a way to retrieve the data stored in the DNA. The storing data is a half of the story. The retrieving it is the other half. Think about it like in a massive library. We don't want to read every single book in the library to find the book that we want. We want to just go directly to the correct shelf and pick it out. And this process, we call it random access. To understand the challenge, let's first look in the digital world. Random access is a solved problem in the digital world. In a device like SSD, the controller knows the physical addresses of the data you want. It can go there directly and retrieve the data quickly and accurately. The whole process is fast and precise. But in the world of DNA, for example, the NGS, we cannot point to the molecules directly, and we need to rely on some PCR-based techniques, such as multiplexed PCR or hybridization capture. These techniques are often slow, and they need complex laboratory procedures. Therefore, we need a faster, smarter way to perform target data readout. And here's the nanopore sequencing comes in. The nanopore sequencing offers the opportunity for us to perform the target data readout. It offers a capability called read-until. The read-until works like this. DNA strand passes through a nanopore, and the system analyzes the sequencing signal in real time. The system will recognize the DNA strand and decide whether to accept the DNA strand or reject it. If the DNA strand belongs to our interested references, the sequencing will continue. If not, the sequencer will reject the strand and start sequencing another one. To make this process be truly practical, we think we need two things. The first thing is easily distinguishable DNA signatures, and the second thing is a rapid decision-making controller. To address these challenges, we present our system called SUSTag-ORC system. This system consists of two components. The first component is SUSTag, which is a set of DNA tags which act as address bits. We designed these tags from the ground up to be easily recognizable by controller. And our controller is ORC, stands for optional rejection, CNN-LSTM with transfer knurling. This is the brain of our system. It can analyze the raw signal and decides whether to accept the DNA strand or reject it. Together, they form a complete solution for our goal of achieving accurate random access. As for the SUSTag design, we design our tags using a unique way. Instead of just looking at the nucleotide sequences, we focus on the nanopore signatures. We compiled all the generated signatures with Euclidean distances and Bhattacharyya distances. The Euclidean distance is widely used to measure the differences between two signals, and the Bhattacharyya distance used by us is to capture the differences between the signal distributions because the nanopore sequencing signals varies even if the nucleotide sequences are the same. And as for the results, we can see our design, SUSTag-96, has most larger minimal distance in Euclidean distance and Bhattacharyya distance than the other two tag design, the ONT69 and the Porcupine69. The Porcupine69, this research is done by Jeff Newalla in 2020. And let's move on to the decision-making model. We built a deep learning model called ORC to make the decisions. We use the CNN blocks to extract the features from the nanopore sequencing signals and send them to the LSTM block. LSTM block will identify every single strand to make the decision. And the most important module in our model is this optional rejection module. This module allows the model to say, I'm not sure about the ambiguous sequences. And as for the results, we can see our SUSTag cooperated with the ORCL model, achieved an impressive weighted F1 score of 99.69%, outperforming other tag designs and other deep learning architectures. Model pre-trained in the laboratory must be applied to the real-world applications. This brings us to the key challenge, domain adaptation. Because of the speed of the sequencing speed is not constant, but the input window of our deep learning model is a fixed length. So the model sees not only the tag signatures we designed, but also the payload DNA signatures. If we applied our pre-trained model to a new data set, like DNA storage data set, the payload DNA signatures will change totally, and these changes will affect the model performance. Let's say the affection, without any domain adaptation, the model's performance drops significantly to about 87 F1 score, and after some fine-tuning with the new data, we can see the model's performance is restored and it achieves over 94% F1 score. For the final experiment we made, we encode the image data and text data using the CHN codec into the nucleotide sequences. And our goal is to retrieve the part of the data which addresses syntax from the number 29 to number 44, which is part of the text data. And to be compromised, we comprise our system with two pipelines. The first pipeline is a Porcupine pipeline. We choose it as a representative pipeline because it's similar with us. It sends the signals directly to the deep learning model and outputs the identification results. The difference is that the Porcupine pipeline lacks of the domain adaptation step, and the other pipeline is a read-fish pipeline. A read-fish pipeline is a mainstream pipeline. These pipelines send the signals firstly to the base callers, such as Dorado, Bonito, and the base caller outputs the nucleotide sequences. The researchers will use some mapping tools to map this output to the references and finally get the identification results. Let's see the final results. You can see without any domain adaptation, the non-targeted data area seems some peaks. These peaks is crosstalk, which can affect our data retrieving. You can see the left panel, the redfish pipeline is very precise, but the data retrieving is incomplete. Our target data is not totally retrieved, and in Pokéline pipeline, the target data is retrieved fully, but it suffered from a very high crosstalk. You can see we put out a lot of non-target data that we don't want. As for our system, SUSTag-ORC, we can see we achieved 100% target data purity and 100% target data recovery. In conclusion, our system made these 3 contributions. We developed an end-to-end framework, SUSTag-ORC, for random access in DNA storage. We designed the SUSTag, a novel set of 384-plex barcodes optimized for nanopore sequencing, and we achieved rapid and PCR-free random access with 100% target data purity and 100% target data recovery. In the future, we plan to adapt our work to the latest R10.4.1 nanopore chemistry, or we want to develop a more powerful zero-shot or few-shot universal model. Furthermore, we would like to expand the new applications, such as targeted sequencing for precision diagnostics. This work presented today is submitted for publication, and the codec system we used, called composite hedges nanopores, I haven't gone into deeply because my lab mate Fan Qingyuan will introduce it later in this session. At last, I will thank all my collaborators and our funding agencies. Thanks for the attention.
Thank you. Very interesting presentation. Question, comment?
Thank you. Thank you for this nice presentation. I was just wondering, while using the read-until approach with the SUSTag, if you have to have all the possible barcodes in your during the sequencing, and what happens if it exists some sequence which are not matching the space of barcodes.
Okay, we designed SUSTag because we think the tag system, just like ONT provided, is not suited for us pipeline because it's too short. Just like I present here, the model input window is fixed and the sequencing speed is fast. So the ONT69 only has 24 base pairs. We think this is too short for deep learning models, so we designed a new set of the tag system, and we proved these tags is a good choice for our deep learning, and you can see these results. It is outperforming. Thank you.
Okay, Thank you.
One more question? No? Yeah.
Thank you for the talk. I had a question regarding the encoding of your signal with the raw signal of the nanopore. If I give you a random sequence, can you tell me exactly the shape of the signal it will make using your model?
This?
Yes, yes.
Okay.
So here I assume you trained the model to recognize these patterns and to encode 384 sequences with distinct signals, right?
This signal I showed here is the raw signal. It is the current signals. We divide these tags by we walk through every 8-mer and then 9-mer sequences, and we use incremental clustering methods to pick out the representative sequence, and we slice them up to about 17 sequence, and repeat the previous step. Finally we got our SUSTag. It has a length of 34.
Okay, I see. So, okay, I will come to discuss with you at the break. Thank you.
Okay, let's switch to the next speaker, okay? Thank you again for this nice presentation. A lot of data.